So thank you all the organizers for inviting me for this conference. And so we have heard a very good talk in the morning about MBE. So today I'm going to speak about a different type of epitaxial growth, that is the van der Waals epitaxial growth, and mainly focusing on growth of 2D and quasi-2D materials. And I will talk briefly about what are the prospects for optoelectronic and spintronic devices. So first let me tell you what is the difference between the conventional epitaxy and the van der Waals epitaxy. So in conventional epitaxy, so you need to have a very good lattice mismatch. And if the lattice mismatch is not great, then you're going to have a lot of misfit dislocations. And so in conventional epitaxy, you cannot go beyond a lattice mismatch of like say 10%. But van der Waals epitaxy is a different type of epitaxy which is governed by the van der Waals force of interaction between the substrate and the epilayer. So in this case, you can actually go to much larger lattice mismatch that has been reported. And also another thing is that these kind of substrates, what we use in van der Waals epitaxy, so these are devoid of dangling bonds. So this helps to grow a different variety of materials as opposed to the conventional epitaxy, which is which is dominated by the lattice mismatch. So let me give you a brief outline of the talk. So first I will talk about the briefly on the epitaxy of 2D and quasi-2D materials growth. And then I will talk about one of the systems that we have recently grown, that is a quasi-2D magnet chromium telluride. And I will talk more about the growth, the non-collinear magnetism, and the prospects for spintronics in this material. And towards the end, if there is time, I will also talk about the WAC2, which is a very well-known 2D semiconductor, but how the growth of WAC2 is dependent upon the substrate on which we try to grow, and how the optical emission signatures are affected by the substrate. And finally, I will conclude and give you some of the future outlook. So first let us get a brief idea about the epitaxy of 2D materials growth. So if you see 2D materials epitaxy, so there are different types. There is a different type of epitaxy that is happening with the 2D materials and the way the 2D materials have been growing. So the first one is the van der Waals epitaxy. So here basically you have a crystalline substrate, and on top of that you have a 2D material which is attaching. There is a van der Waals force of interaction between the epilayer and the substrate, and you start growing this material. So this will be the topic of this talk, and I will discuss this more. But there are other interesting kind of epitaxy as well which you find in 2D materials. So for example, you have the edge epitaxy, and this is seen mainly in growth of graphene or HBN on substrates like metal. So what happens is the edges of the 2D materials are highly reactive, and they can form a very strong bond with the metal atom, with the metal substrate. So depending upon that, the direction or the symmetry of the metal, so that will basically decide what is the growth direction, what is the morphology of the grains that are growing. And this basically arises because of the edges, and that is why it's termed as edge epitaxy. Then you have step guided epitaxy. So in many of the metal surface or many of the crystalline substrates, you see that there are these terraces. So these terraces will act as points where the 2D material starts attaching, and from there you will see that depending upon the symmetry of the substrate, you will start seeing the growth of the 2D material. So this is what is called as step guided epitaxy. And finally we have what is called as the in-plane epitaxy. So in-plane epitaxy is something which is more like the conventional epitaxy. And in in-plane epitaxy, you need to have a good lattice matching parameter for the edges. So for example, if you are having MOS2 and WS2, so the lattice parameters for the edges are almost the same. And you can see that there is a good covalent bonding at these edges. And these basically form what we call as in-plane van der Waals heterostructures. So now I'm going to go more in detail about van der Waals epitaxy. So this is the initial phase where people were trying to grow lot of the 2D materials on top of different substrates. And so we start with the epitaxial growth of graphene on HBN. So once you grow graphene on HBN, you can see that the crystals, you see that the edges of the crystals are having good alignment. And if you do STM studies or TM studies, you can see that you have a moire pattern that is arising between the graphene and the HBN. Okay, so this is again, this shows that there is some kind of an epitaxy that is involved in this growth. And the other kind of materials what people have been growing using chemical vapor deposition. So this is basically the vertical heterostructures from WS2 MOS2 monolayers. So if you see, you have MOS2 layer, and then on top of that you have now another triangle that is forming, which is again a WS2 layer. So you can see that this is like one triangle over another and with exact parallel edges. So again, this is another kind of epitaxial growth that is happening. And one good thing about these kind of heterostructures is that, so we have heard talks where you place one material on top of another and then you try to study the interaction. But as opposed to that, if you have vertical heterostructures that are grown using CVD, now the interlayer coupling is very strong and you start seeing features which are not present in the directly stacked heterostructures. For example, you can start seeing features like the interlayer excitons, you start seeing features in the Raman. So this is like what people were doing with van der Waals epitaxy, and in these cases you see that the materials that were grown did not have too much of a lattice mismatch. But you can also grow materials with large lattice mismatch as high as 50%, and also between materials having different crystal structures. So these are some of the examples for that. So for example, you take this study where they have tried to grow this WSE2 and SNS2 vertical heterostructures. So you can see that both WS2 and SNS2, they have completely different lattice parameters. So if you take the TM diffraction image of these kind of heterostructures, you can calculate what are the lattice constants from the diffraction planes, and you see that there is a very large mismatch. But how in these kind of systems the second layer is growing? So is it possible? So that is a question what we have also tried to ask. So one of the possible things that can happen is, so there is a commensurate lattice that is getting formed. So there are certain regions or certain crystallographic orientations where there are minima in energy, and the second layer will try to grow along those particular orientations. So this is one example. Then also we can see other examples where these kind of transition metal dichalcogenic monolayers were grown on mica and sapphire. So mica is a very good substrate for growth, because just like the van der Waals materials like graphene or HBN, so mica substrate is atomically flat, and also it is free of dangling bonds. So you see that you have these kind of nice epitaxial growth, well aligned triangles of TMD monolayers that are forming on mica and sapphire. So these are cases where you have a pretty large lattice mismatch, but still you can get a good amount of epitaxy. So how to modulate this van der Waals epitaxy? So there are mainly three factors. The first one is the temperature, then you have the precursor concentration, and lastly you have the substrate symmetry. So these are the three important parameters which will govern whether you are able to grow a nice epitaxial 2D layer or not. So first thing is the temperature. So if you see, as I told you, so there are certain crystallographic directions which are preferred when one layer is trying to grow over the substrate, and depending upon that, so depending upon what is the temperature, So the nuclei that are forming, they can rotate and they can align along the certain preferred directions. So if you see in this graph, you have the minimum binding energy for 0 degree and 60 degree. So mostly when you are in the right temperature regime, you will see that you are having triangles which are having 0 or 60 degree orientation. Now the next one is the precursor concentration. So it's not that all the time you have to go to higher temperatures and you have to overcome this rotational barrier and have this to facilitate this van der Waals epitaxy. There are other ways to do that. For example, you can do it at much lower temperatures by giving a larger inflow of your precursor gases. For example, so if you have this study shows that so in the growth of MOS2, if you increase the amount of sulfur precursor, you see that you can have in a small nuclei which are forming, and these small nuclei, they rotate and they align along the preferential direction, and you get well aligned domains. So the third important point is the substrate symmetry. So why we have certain directions which are preferred? So this comes from the fact that there is a strong correlation with the substrate symmetry. So depending upon what is the symmetry of the substrate, so you can have growth in certain direction along certain lattice directions, as well as that also defines what is the morphology of the crystals that are growing. So let me explain this a little bit more, because this is one of the important aspects that one looks at when you try to grow these 2D monolayers, because you always want to have nice, if you have grown graphene or the TMDs, you know that you always look for nice hexagonal or triangular flakes which are like perfect triangles or hexagons. So why you get these kind of hexagons or triangles? So that is basically dictated by the symmetries of the 2D material and the substrate. So what happens is, so if you, let me illustrate this with the case help of graphene and HBN. So graphene has the symmetry of C6V and HBN has slightly lower symmetry of C3V. So if you take the graphene and HBN growth on copper, so along the different planes, so you can see that along the 110 plane, you have basically the slowest propagating mode in graphene has been shown to be the zigzag edge, whereas in the case of boron nitride, it is the nitrogen terminated zigzag edge. So you see that these are the modes that are propagating, and they will propagate along these particular crystal directions. Okay, so this propagation is determined by the symmetry of the substrate. And if you go to 110 plane, then you can see that there are, for the case of graphene, you have two possibilities. So there is 0 and a 30-degree rotation is also possible, and these are degenerate. So if you try to grow on 110 copper, you will see both these kind of orientational hexagons that are growing. And if you grow on 110, again, this is the kind of the hexagon which will be oriented. So depending upon this, you can see that there are, so if you take the case of HBN, you see that along certain directions, you can have 4 possible, orientations. Now, why is it important to study these kind of orientations? So in the case of graphene, it is still okay, because if you are trying to grow on 110, so this is the only orientation that is possible. So if all the grains, all the domains are in this growing along this direction, they will finally coalesce and you will get a very large single crystalline graphene. But if you take the case of HBN, now there are 2 possibilities, one is 0 degree and one 60 degree. Now what will happen? So when these now try to grow, these two can combine and you start getting twin boundaries. So instead of getting a perfect single crystal in the case of graphene, in case of HBN, you start seeing a lot of twin grain boundaries, which is not good for the transport. Okay, so same is the case with other TMDs as well. So that is why it is important to see how you can arrest the growth of one particular orientation, and you can assess the growth of the other particular orientation. So there are, so this is giving you some of the experimental observations of what I have just told you. So as you see, this is graphene which is grown on copper 111. You have only one alignment that is possible. This is HBN on copper 111. So you can see there are this 0 and 60-degree domains. And on copper 100, along with these, you also have these 30-degree domains. But there was another study on MOS2 on HBN, growth of MOS2 on HBN. So which was very interesting, because what they could do was they could preferentially grow only one particular orientation. And what they had done was, so the HBN, that was a substrate, they were introducing a lot of substrate defects into this HBN. So there are nitrogen vacancies or boron vacancies, and depending upon the type of the vacancy, you can either have, the 0-degree or the 60-degree domains that are forming. So this is another way in which you can control the van der Waals epitaxy in these kind of 2D materials. So with this introduction, now I would like to talk more about one of the material that we have been studying of late. So that is a quasi-2D magnet chromium telluride. So why this? So what are these quasi-2D materials? Why these are not called 2D materials but instead quasi-2D? So if you see, 2D materials are classified, are basically defined as atomically thin layers, and these are interconnected by the van der Waals forces. But when you talk about quasi-2D materials, what happens is you have these layers here, just like you had in the earlier case, but also you have some atoms which are there sitting in between these layers. And these atoms can now have covalent bonds with the atoms in the two layers. And because of that, this is not a strict van der Waals material, this is a non-van der Waals material with covalently bonded intercalants. So chromium telluride is such kind of a material, and what makes chromium telluride interesting is, so before I go to that, so let me first quickly tell you about how you can grow these quasi-2D materials. So quasi-2D materials growth is not very trivial, because so this question arose when I was doing my postdoc. So mostly we were able to grow all these chalcogenides like MOS2, WS2 in thin layers. But as soon as we tried to grow some other chalcogenides like say vanadium sulfide, rhenium sulfide, it was very difficult to grow them in monolayer form. So that is where this thing came to my mind. So how to tune the thickness of these these layered materials and how to grow them controllably. So for that you need to understand what are the different type of growth mechanisms that are possible in crystal growth. So the two things that can happen, one is basically what is the addition of the add atoms to the substrate, and the other important thing to note is what is the diffusion barrier for these add atoms on the surface. So these are the two factors that will decide the type of the growth mechanism. So if you take the first case, so if suppose you have a substrate on which the add atoms can easily adhere to, like for example the case of a van der Waals material, because they don't have any dangling bonds, they don't have surface roughness, so easily the add atom is coming and adhering to the van der Waals surface. And in this case you also have, these materials also have very low diffusion barriers. So because of that, what happens is, so the atoms, so initial nucleus forms and the next set of add atoms then start attaching to this edge sides of the nucleus, because these are more reactive than the planar side. So the addition energy here between the substrate and the add atoms are more than this cohesive energy between the add atoms, and also because of this diffusion barrier, low diffusion barrier, so these atoms can nicely disperse through and form thin layers. And this is basically called as Frank van der Merwe type or layer by layer type of growth. So this is one growth mechanism which is important when you try to grow these van der Waals materials or quasi van der Waals materials. Now the other case that can happen is the Volmer-Weber growth, And in this case, what happens is, so you have a very large diffusion barrier. Like for example, you take the case of sapphire substrate. So it is not very smooth like the, like say HBN surface or so. So because of that, you have a very large diffusion barrier. So the atoms which are getting adsorbed, so it cannot now move to the other regions. They cannot spread over the substrate, and instead of that, more and more atoms start attaching on top of the initial layer that is formed, and because of that, you start seeing small islands, which then increase in thickness, and you basically get a 3D structure rather than a 2D layer. So this is, so mainly, so it's basically a tuning between the kind of the substrate and the growth parameters, where like the temperature, the precursors, which can finally tell you what will be the type of the growth mechanism. Now, so there are again, you can divide the kinetics of the growth into two types. One is the attachment limited growth and the other is the diffusion limited growth. So these kind of figures you might be familiar with, people who have been doing CVD and of 2D materials. So some cases you might have seen very nice polygonal shapes, whereas in some cases you see these kind of fractal shapes. So why does, why do you get these kind of different morphologies for the crystals? So for that, we have to understand the two types of growth mechanism. So the first one is the attachment limited growth. So here the main condition is that the precursor concentration over this whole substrate has to be maintained a constant. If that is the case, then what happens? The precursor is going to attach only to the edges of these initial nuclei that is formed, and so the growing edges of the 2D material will keep growing, and you get nice large single layers of the 2D material. But what happens is, in certain, under certain conditions, like say when you are at very high temperatures, or if you do not have enough precursors in your system, so you can reach a point where there is a depletion, there's a local depletion of the precursors in the growth region. So in this kind of situation, what happens is there is like a barrierless attachment of the precursors at the edges, and because of that, there is basically the precursors in these regions get depleted, and the growth will be basically determined by the diffusion of atoms or molecules on the surface. Okay, so it is mostly determined by the temperature here. So in that case, you get these kind of fractal shapes, and mostly when you are growing these 2D materials using chemical vapor deposition, you want to be in this attachment limited growth where you can get high crystalline quality for the material. So this is basically how you can define the rate of growth of these edges. So in this equation, so the main important parameters are basically nu is the attachment or desorption factor, and EBA and EBD are basically the energies, binding energies for the attachment or detachment of the precursors, because these are both the processes are possible. You can either have precursors attaching, or you can have the precursors detaching from the substrate. So this is basically a competition between these, and if you want a good growth of the material, then this energy difference between the detachment and the attachment should be less than kT log C by C naught. So here C is the concentration of the precursors at the edges, and C naught is the equilibrium concentration of precursors on the substrate. So this is a condition for the growth of the material. And if you want to have attachment limited growth for obtaining these kind of 2D single crystal, so there are three conditions to be met. So the first one is the atomic attachment or detachment should be very slow. That means these energy barriers should be very large, so that there is no sudden attachment and depletion of the precursors in the growth region. And the second one is diffusion of atoms on the surface, on the substrate surface is extremely fast, so that the precursors, whatever precursors are adsorbed, they can immediately attach and come to the growth zone and start attaching to the edges. And the third one is atomic flux is sufficiently large, and this has to ensure that you have a continuous growth that is happening in your system. So what we try to do is, when we try to grow using CVD, we try to maintain these conditions so that you get very good crystals of 2D materials. So now coming back to the material that we'll be looking at. So this is the chromium telluride system, and as I told you, this is a very interesting system because it has a large number of stoichiometric phases. So chromium telluride, CrTe2, is basically a layered material. So it has two chromium telluride layers, and what one can do is you can start including more and more chromium atoms which will go and intercalate between the two layers. Okay, so this is called as chromium self-intercalation, and that can based on what is the concentration of the chromium atoms in the intercalated position. You can have chromium Cr5Te8, Cr2Te3, Cr3Te4, Crt. So these are different stable compounds of chromium telluride. And also this material is interesting because some of these compounds also show room temperature ferromagnetism, and definitely above 77 Kelvin. And also, even though here these materials, I have shown that they have inversion symmetry, some recent results using single harmonic, second harmonic generation and XRD have shown that many of these materials do not possess the inversion symmetry. So these are, because of that, there are several interesting implications for magnetism. And so first we will start with the growth of these materials. So this is basically grown using chemical vapor deposition with the precursors tellurium and chromium chloride. And so the chromium chloride is basically kept at a temperature of 670 degrees Celsius, while tellurium is kept at 400 degrees Celsius. And under hydrogen and argon gas flow, we carry out the growth. And initially we started the growth on silicon oxide substrate, and we always used to see these kind of nice bulk hexagons which were forming. And in order to, we don't know initially what is the stoichiometry, so we have tried to characterize these materials by using XRD and energy dispersive spectroscopy. So from the indexing of these peaks, one can know that this is Cr5Te8, and also from the EDS you can calculate what is the atomic percent, and that also shows that it has a composition of Cr5Te8. Excuse me. So now the question is, how do we grow these in thinner form? Okay, so we tried several substrates what we had. So one was silicon 100, then we tried on sapphire, but we did not have much of a success. So then we decided that we will try growing them on van der Waals substrates, like say you can mechanically exfoliate graphite or HBN, and we can try the growth on that. So if you strain your eyes a little bit, you can see some of these light patches on top of this graphite, and these are actually the Cr5Te8 crystals which are growing in very thin thin layer. And the same thing we can also try on HBN, where also we see that we are able to significantly thin down from this kind of a system. So this is another interesting thing which you will notice in this figure is that, so as soon as we put in a van der Waals substrate, so the chromium telluride actually stops growing on the silicon oxide. We do not see any growth on silicon oxide, whereas we see all the growth which is happening on graphite or HBN. So this is also very interesting, and this shows that the van der Waals substrates are most suited for these kind of growth. So we can also do Raman spectroscopy. So the Raman spectroscopy on HBN and graphene actually shows that there is a shift in the spectrum because of the thickness. So the thinner samples showed that the spectrum, both the A1G and the EG peaks are shifted. Now the question is, so why graphene and HBN is helping in van der Waals epitaxy? So for this, what we did was, the first calculation that was done was to calculate what is the lattice misfit between chromium telluride and graphene and HBN. So if you see, the misfit is very large when you calculate for graphene and HBN. It is almost close to 65 to 70%, whereas it is very less for sapphire. But still we are able to see that, graphene and HBN we are able to grow this chromium telluride. So if this is the case, then how this growth is happening? So, and what is there any kind of alignment, any kind of directionality which is involved in this growth? So one thing that is clear is, so basically on sapphire, since we see only the 3D, we can attribute it to the island growth mechanism, which I explained, and in the case of graphene or boron nitride, we are basically seeing the layer by layer growth. Now the interesting part was when we did the TEM, and high resolution TEM of these heterostructures. So the samples where we had some very thin graphene and HBN on which we could grow this chromium telluride, and on looking at these structures in the HRTM, we could see nice moire patterns that are emerging. And this is basically the FFT of that. So you can see that you have this hexagonal symmetry, and along with that you have some satellite peaks around that. So this is generally seen whenever you have a moire superlattice, and in this case what we see is once you index this, you see that, so this set of peaks correspond to the 220 plane of chromium telluride, and the yellow one here corresponds to the 010 plane of graphene. So what happens is, so the system is actually trying to align in such a way that it is having a commensurate structure. Even though you have a very large lattice misfit between the two lattices of graphene and chromium telluride, so there is a commensurate lattice that is formed once you try to grow them on top of another. And you can actually calculate the moire wave vector, the moire period from this using this expression. So here alpha is the lattice constant of graphene, delta is the misfit between 010 and 220 planes of these, and phi here is 0 because in this case there is no rotation, no apparent rotation between the two planes 010 and 220. And if you put in this value, you find lambda is equal to 2.48, and that matches well with what we see in the real space. And similarly, we have also calculated this for the case of HBN, and in case of HBN also we see that it is matching well with the moire pattern that is formed in the real space. So this confirms that even though you have a very large lattice misfit, the growth is basically happening along a certain commensurate direction. So also we have seen what is the effect of different growth parameters. One is the temperature. So with temperature we can see that as you go to higher and higher temperature, the epitaxy is better. And also we can try some other kind of precursors, like for example, you can try to do salt assisted CVD. So you can mix NaCl with chromium chloride, that basically reduces the sublimation temperature of these precursors, and you see well aligned domains that are formed in this salt assisted CVD technique. So now coming to the magnetic aspects of this material. So first of all, let me tell you that in this material now we have chromium and we have tellurium, two different atoms, and the spin is basically the spin moments of the chromium is what we are trying to consider. Now what are the different mechanisms by which you can have an exchange interaction here? Either you can have a direct exchange interaction between the two spins here on chromium, or you can have a conduction electron mediated exchange interaction, or you can have a super exchange interaction which is mediated through the tellurium. Okay, so this is, so if you are considering the direct exchange, it is basically an antiferromagnetic chromium-chromium direct exchange interaction. Whereas if you consider the super exchange, it is basically a ferromagnetic interaction between the chromium telluride chromium unit. So what is interesting between the CrT2, which is a layered chromium telluride, and the other systems where you have now a chromium intercalent is that, so you are basically modifying the type of exchange interaction. So in this case, you have only one type of exchange interaction, that is J11, which is the intra sublattice exchange interaction. Whereas in this case, you can have J11, so that is between the chromium atoms in the layer. Then you can have J22, that is the exchange interaction between the chromium atoms which are there in the intercalent chromium atom. And you can also have J12, which is now between the sublayer and the intercalents. So depending upon that, what we see is that, so when delta is 0, that means there are no intercalents, chromium intercalents, you see that the spins are all nice and ferromagnetically aligned. But as soon as you start introducing these intercalents, now what happens is, so there is now the angle between chromium and tellurium is going to increase, and that also introduces in plane spins here. So this basically gives rise to a non-collinearity or a spin canting for the case of the chromium telluride which are having intercalents. So this is interesting because we also see effects of this when we do the squid measurements. So mind you, these are the squid measurements which are done on the bulk samples. So bulk samples, we can see that you have a Curie temperature of around 175 Kelvin, and again we see a small increase, a small point here where you see there is a transition. So this we attribute it to the two different exchange interactions that I just talked about. So one is between the exchange interaction for the chromium in the sublayers, and the other one is the exchange interaction energy for the intercalent chromium atom. And you see that there is a large perpendicular magnetic anisotropy also, which is coming from this MT curve. So this is the hysteresis curve, which again shows that these are ferromagnetic. And here the hysteresis is done with field perpendicular to the AB direction. The field parallel to the AB direction, the MH curve look very interesting because we see that there is a small kink near the zero field. So this can be explained by the fact that, so once you apply a high magnetic field, so all the spins of the chromium 1 and 2 are all aligned along the field. But when you reduce the field to 0, so first of all you see that the chromium 1 atoms, the spins of chromium 1 atoms are trying to come back to the EC direction, whereas the spins on the chromium 2 are still canted. And then, so you have to apply a coercive field in the opposite direction to make all these spins go to the EC direction, and same thing happens in the negative field direction. So as you increase the temperature, you can see around 70 Kelvin, this kink starts reducing, and above 150 Kelvin, where we believe that the spins on the chromium 2 atoms have been randomized, we see that there is a single hysteresis curve that is present. So this is again evidence for the non-collinearity in this system. Now why the system is interesting? Because several studies have shown that these kind of systems lack inversion symmetry, and if you have systems where there is which lack inversion symmetry, so you can have an additional contribution to the total magnetic exchange interaction which is arising from the antisymmetric exchange or the DMI interaction. So, and especially when there is the exchange interaction is mediated by a material or atom which is having very large spin orbit coupling, you tend to see this DMI interaction. So this can give rise to these kind of skyrmions, and these skyrmions have been observed in thin cross sections of chromium telluride. and also there are reports of topological Hall effect which are arising in these kind of materials. So this actually makes the system very interesting as to study the the skyrmions and any other kind of chiral magnetic structures that are forming. So now quickly I'll just go through some of the last part of the talk. So again we have tried to grow this WAC2 again on different kind of substrates. So these are under identical conditions. You can see the growth on SiO2 as well as sapphire. So on sapphire you see that you get very nice monolayers, whereas you start seeing bulk when you grow on silicon oxide. And this is again something which we have tried very recently. So we have tried growing the WAC2 on top of HBN, and here also we see that we can get almost monolayers here. So now the interesting thing is, so because you get mostly monolayers on sapphire, so in the CVD community people try to grow most of these TMDs on sapphire rather than silicon oxide. But the thing is, what we have seen is, so this is basically the spectroscopic signatures of these flakes which are grown on different substrates. So this is the one on sapphire. So if you see the PL intensity map, you see that certain places the PL intensity is high, certain places it's quenched, whereas on silicon oxide it is mostly uniform except at the edges, which people have attributed to possible formation of bi-excitons and stuff. And on HBN also we see that there is kind of slight variations in the PL intensity. But what I would like to focus more is what is happening on sapphire. So you can see that this is a peak in PL intensity map, and this is a map of the PL peak. So how the PL peak is shifting. You see that in this region, so the peak is shifting towards the higher energy, and here the peak is shifting towards the lower energy. Now, so one more thing what we did was we tried to study the Raman. So Raman also showed that in these regions where you are having this PL peak shifting, you see that there are anomalies in the Raman. Raman also shows a shift. So this is what we tried to, and this you can see in many other samples that we have grown on sapphire. So one of the possible reasons why on sapphire this is shown is sapphire has basically very high thermal expansion coefficient. So when you are growing this material at say 700 or 800 degrees Celsius and you try to lower the temperature, so there is a compressive strain because of the thermal shrinking of sapphire, and that can give rise to these kind of effects. So interestingly, what we see is if you plot the Raman intensity at these different points, you see that at point 3 where the PL look more or less uniform, the Raman peaks are also good. But if you go to the point 2, you see that there is a small shifting of the spectral weight here. And if you go to point 1, you see that there is clearly peak splitting in the Raman. So this is something which one can explain in terms of strain. So the blue one here is the unstrained condition for WAC2. So here you see that the AG and EG modes are almost degenerate, and when you apply a strain, you see that the E prime mode, it basically splits into E plus and E minus, and this is basically the E minus mode which is getting more and more Raman shifted, which we can pick it up. And the last thing what I just want to show you here, so that is about the Raman. So we see that there is definitely a strain component that is present. And another thing is, so along with that strain, we also see in one side the PL was quenching, other side PL was enhancing. Also the peak was getting shifted. So if you take the spot PL spectrum, what you can see is, so the region 3, so the region 3 is here. So this is a PL for the region 3 where there is no strain. For the region 2, we see that the PL is shifted as well as shifted to higher energy, as well as there is a reduction. And in region 1, it is shifted towards the lower energy, but there is an increase in the intensity. So this can be explained by changes in the band structure that can happen when you apply this uniaxial tensile and compressive strain. So in one case, when you are having the tensile strain, your band gap is reducing, whereas in the other case, now your band gap is increasing and you start seeing more effects from the indirect band gap transitions. So with this, I will conclude. So I have told you about the van der Waals epitaxy, the growth mechanism and prospects for large area growth of 2D and quasi-2D materials. Then we have particularly looked into a chromium telluride system, and it is a very interesting system, and the next plan is to look into what happens to these fermions when you have magnetic Moiré superlattice. And I have also talked to you about the substrate interactions in WAC2 when you try to grow them on substrates which are having large thermal expansion coefficient. So with this, I would like to acknowledge my group members. So he is the guy, he's my MTech student. He was my MTech student who did most of the work on chromium telluride. And I would like to acknowledge all the funding, facilities, and my collaborators. Thank you.
Okay, now the session is open for questions, comments. Yeah, here. So you should speak up or
Ma'am, you showed in the starting that the heterostructures can be formed if their lattice mismatch is 50%, and you gave an example of WSE2 and SNS2. So in that heterostructure, and there is a Moiré pattern also. So that Moiré pattern is due to the lattice mismatch only, or there is a twist between the angles?
So the idea of van der Waals epitaxy is that even if you are trying to grow two different materials which are having very large lattice mismatch, so there is the system or the epilayer will try to rotate towards the lowest energy configuration, where by which it can minimize this lattice mismatch. The same thing happens on the case of mica also. Even though you see that if you just put one lattice over the other, you have a very large lattice mismatch. But what happens is the epilayer will try to rotate to the least energy possible. So it could be like 30 degrees or in some cases 60 degrees.
So the lattice or the layers get strained is like.
Yes, the idea of forming the commensurate lattice is to reduce the strain.
Okay. And another question is related to
maybe check
CRT.
if you have more questions.
Just one question.
Right.
In that CRT2, the magnetic anisotropy or the easy axis is along the Z direction?
Along the C axis.
Okay, thank you.
Hello, ma'am, you are talking about the Raman shift and PL shift in the like two different materials. So I'm asking that how much Raman shift is acceptable? How we know that this Raman shift or this PL shift is accepted like compared to literature data and anything?
So it is actually not about acceptability. It is like, see, what I showed you here is when you try to grow this 2D material on top of sapphire. So once you see that there is this kind of a Raman shift, it shows that because of this Raman shift, the optical properties are significantly influenced. But you can always have the option of transferring this to a new substrate. But it becomes important when you're trying to grow directly these heterostructures. For example, directly if I'm trying to grow WSE2 on top of HBN, and if these kind of lattice strain factors are affecting, then it is going to be important to look at.
And ma'am, this is like surprising that when we grow on the HBN substrate and like graphite, you told that the growth is only happened on the HBN, not on SiO2.
Yes.
And the similar, when we grow on the SiO2, then growth is like there.
Yeah.
So ma'am, what is the reason behind this?
Because actually for the van der Waals substrates, the adhesion energy is much smaller. So easily the precursor atoms, they can come and attach on the van der Waals substrate than the other kind of substrates.
So, ma'am, like in PL and Raman shift, yeah, we usually say that this is phase engineered, like phase engineered material, just because there may be a strain and there may be defects.
Phase engineering is when you go to a completely different structural phase, right?
No, ma'am, like when you told that when we have Raman shift, like maybe PL shift, so we can say that there is a strain,
Yes.
inbuilt strain in the
Yes.
material.
Yes.
Like sometimes we say that maybe there is a defects on the for the shift. So how we confirmed that this is the strain only?
Yeah, so strain actually affects the EG modes, okay, whereas E2G modes, whereas the if you are having defects or any kind of dopants, those affects the AG modes. So the AG modes don't shift when you apply a strain because they are the out of plane modes. The in plane modes are what are affected by the strain. The AG modes actually are affected by the dopants, and also so you have to have a correlation between the Raman and the PL to understand this completely. So if you are seeing that there is a shift of the AG mode, then you can try to fit your PL peak with more of the trion contribution and see whether there is some doping which is happening or not.
Okay, ma'am. Thank you.
Okay, thanks. I think we are
Yeah.
actually quite late. So, well, thank you all for the patience. So see you later.